Hello again. In this video, I'm going to go over this homework problem from 4.5. So in this problem, it says, suppose an airline policy states that all baggage must be box-shaped with a sum of length, width, and height not exceeding 60 inches. What are the dimensions and volumes of a square-based box with the greatest volume under these conditions? And then we're supposed to write a function for the volume of the box in terms of W, where W is one of the edges of the square bottom. Okay, so let me show you how to work this out. So first of all, this is a picture of the box. Remember, it has a square base, so this distance here is the same as this distance here, and I'm just going to call that, they said to call that W. And then this is the other distance, which I'm going to call L for length. So that's what the square-based box looks like. Now, this is an optimization problem. Anytime you work out an optimization problem, you should probably first write down the objective. And it's either to maximize some quantity or to minimize some quantity. And of course, in this case, we're trying to maximize the volume of this box. So that's our objective. And then you should probably think about what the volume is equal to in terms of some kind of equation. And of course, it's just W times L. Length times width times height. But since this has a square base, the two W's here, right, these are the same length. And so that's W squared times L. Okay, so that gives you the volume of the box. But you also need to look for the constraint equation. If you just want me to maximize the volume of this box, and you don't give me a constraint, then I'm just going to make the length, the width, and the height of the box infinite, and that'll give me infinite volume. Okay, so there must be some kind of constraint, otherwise the maximum volume of the box would be infinite. Okay, well, there is a constraint in this case. The policy of the airline says that the sum of the length, width, and height cannot exceed 60 inches. So that's your constraint. So if we add up these three distances, right, we cannot exceed 60 inches. So W plus L, that would have to be less than or equal to 60. Okay, but I think it makes sense to write this as an equal sign, because if you want to maximize the volume of the box, you're going to try to use as much of this 60 inches as you possibly can. So you're actually going to make sure that the sum of these three actually equals 60. It wouldn't make sense to have it be less than 60, because you want the volume of the box to be as big as possible. Okay, so let's write this as equals to, and then this is just 2W plus L. So that's our constraint equation. Okay, once you have the constraint equation, our next goal is to try to get this objective equation written in terms of one variable. Right now it's written in terms of W and L. Now, using the constraint equation, we can actually get this objective equation written in terms of just one variable. So what I'm going to do here is solve for L in this equation, and then substitute it in for the L in the objective equation. Okay, so to solve for L here, you can just subtract the 2W over to the right-hand side. So L is equal to 60 minus 2W. And then I'm going to substitute that in for this L up here. And now the objective equation is written in terms of one variable, W. Okay, and we can simplify this by distributing the W squared. So this becomes 60W squared minus 2W cubed. Okay, so that's our objective equation written in terms of one variable, W. And then our goal is to take this function and maximize the volume, the output of this function. But before we do that, we really should think about what the domain of this function is, because it's going to be important. Okay, we need to know what input values are allowed for this function before we can maximize the volume. Okay, so we're going to look at the domain of this function. Well, W represents something, right? It represents this distance. So how small could W possibly be? Well, it can't be negative, obviously, because distances can't be negative. So I think the smallest it could possibly be would be 0. It doesn't make sense for W to be a negative number in this context because it represents distance. Okay, well, what's the largest W could be? Well, at first you might think the largest it could be would be 60 because you can't exceed 60 inches. But I think we can get it smaller than that. Because what you're doing is, obviously W could shrink down to 0, and that's the smallest W could be. But it's also possible to let L shrink down to 0. That's the smallest L could be. And if that were to happen, what would you be left with for W? That's really the question. Okay, so if you let L go to 0, let's go back to this equation here. 2W plus L equals 60. If L is 0, which is the smallest this length could be, then that means W would be 30, right? Just divide both sides by 2. Okay, so if L is 0, that means you would have a base that looks like 30 by 30. So that's the biggest W could possibly be. It can't be 60 because you have to have the same length here as you do here. Okay, so it has to be 30 by 30. Okay, so that's the largest W could be. So this is the domain of your function. And then all we're going to try to do now is find the absolute maximum value, output value, for this function on its domain. Well, we've done this before, right? How do you find the absolute maximum on some closed interval? Well, remember, absolute maximums can either occur at the endpoints or at critical points in the interior of the domain. Okay, so what we're going to do is we're going to check the volume, the output of this function at both the endpoints, which are 0 and 30, and also at any critical points in the interior of this domain. Okay, so we still need to find the critical points. Okay, now, how do you find the critical points? Well, remember, critical points are places where the derivative is 0 or doesn't exist. Okay, so let's find those. All right, so first the derivative. Well, the derivative looks to be 120W minus 6W squared. And then we're going to look at both cases, when it's 0 and when it doesn't exist, because those will give us the critical numbers. And of course, this never happens. I can plug any number in for W, and I'm going to get something out for the derivative. So this never happens. This derivative exists for all values of W. Okay? It's also a polynomial, right? Polynomials exist everywhere. Okay, the domain of a polynomial is minus infinity to infinity. Okay. Okay, so that we don't get any critical points from this particular case. Okay, but let's look at this case. So let's take the derivative and set it equal to 0, and then solve for W. Okay, well, to solve this, it's a quadratic equation. You put it in standard form, so one side's equal to 0, and then you want to factor this other side or use the quadratic formula. But I think this factors. You can pull out, it looks like you can pull out maybe a 6W, and that will leave you with 20 minus W. So let's double check that. So this gives you 120W, and this will give you minus 6W squared. Okay, and then just solve both of these by setting them equal to 0. So here you divide both sides by 6, and you get 0 for W. And then this one, of course, you set it equal to 0, and then add W to the other side, and you just get W is equal to 20. So at first, it appears that there are two critical points here, but technically this one is not a critical point. So we're going to eliminate it. Okay, why is it not a critical point? Because critical points have to be in the interior of the domain of the function. And this is not in the interior. This 0 is at the endpoint. So the only critical point we have here is 20, and that is in the interior of the domain. Okay. Okay, so then we're just gonna, again, we're gonna check the endpoints and the critical points and see which one gives us the largest volume. In other words, the largest output for this function, right, our objective equation. Okay, so let's just plug those in and see which one gives us the largest volume. Okay, obviously if you plug 0 in for W, you get 0 out for the volume. And that makes perfect sense because that's the case where the base of the box is like 0 by 0, and it doesn't matter what the length is. I guess it would be 1/6 or 60 because that's what's left over. But that box has no volume, right? The volume of that box will be 0. So that makes perfect sense. All right, what about 30? So let's check that on the calculator and see what we get. So an easy way to do this on the calculator is to go to your y equals button and then clear out anything that's in y1. And then you can type this function in to that, into y1. So 60, and there is no w here, so I'm just going to use x squared, x, and this is the squaring button, minus 2 x cubed, and that's the raising button right there, cubed. Okay, so you just type that in, and then you may want to adjust your window. So for us, this goes from 0 to 30. That's our domain. Okay, that's our input values, or the range for our input values. And then for the output, I guess, the smallest V could be would be 0 for volume. You can't have negative volume. And then it's hard to know how large this might get. So just put in a really large number, okay, which I've done here. Okay, so I think this might be a pretty good window. And then once you've adjusted your window, then you can go and use the calc button. So go to the second button here and then calculate or calc. And then you want to select value, so press enter on that one. And then it'll prompt you for the x value. Okay, so in this case, we're trying to find it when the x value is 30, right? When W is 30. And then press enter, and you can see that you get 0 out. Okay, so the volume in that case would be 0. Well, that makes sense too, because if both of these are 30, right, W is 30 and that one's 30, then there's nothing left over for the length because you've used all 60 right here. So that means the length of this box would be 0, and of course that box has no volume. Okay. So obviously these aren't going to give you the largest volume. Okay. So let's try the last one, which is 20. So again, you could just go to your, once you've entered this into the y equals button, you can just go back to calc and then select value and then put in 20 now for x. And you get 8,000 out, okay, for your volume. Okay, and so obviously this is the largest volume. This is the absolute maximum. Okay, and then maybe to just finish this off, it's probably a good idea to go ahead and describe the dimensions of the box. Okay, so W is 20. So the base is 20 by 20. And then you just have to figure out what the length would be. And if you could probably figure it out, but you could also go back to this equation right here and solve for L. So I'm just going to do that. So L is 60 minus 2W, and we know W is 20. And so you get 60 minus 40, which leaves you with 20. And that happens to be, a perfect cubed, 20 by 20 by 20. Of course, that's going to give you the optimal box to give you the greatest volume would be a cube. So that makes perfect sense now that you think about it, right? All right, so the final answer here is you want a 20 by 20 box, 20 by 20 by 20 box. And when you multiply those dimensions together, it gives you the volume, the maximum volume, which is 8,000. Okay, and let's just double check this. So this is our objective equation. This was the domain that we came up with for the objective equation. And then it's a 20 by 20 box, 20 by 20 by 20 box. And that gives you the greatest volume, which is 8,000 cubic inches. Okay, so I hope you found this video helpful. I'll continue to work out problems from chapter 4, and hopefully you'll get a chance to look at some of my other videos from chapter 4. Until then, bye-bye.